So this video on module over PID, the lecture 8 on module theory. So this is very important in the sense that PID is some nice structure, and module over PID is some sort of very nice property similar to a vector space. So that's why the module over PID is also important. So that should be sorry, that should be module over PID, not simple module. That should be module over PID. So module over PID. So what is PID? We know the PID is the full form of the PID is principal ideal domain. That means in the ring, which must be a domain. So what is domain? We know the domain is AB equal to 0 implies either A equal to 0 or B equal to 0. Obviously commutative and with 1. Commutative and domain with 1. So it is ring with one identity, commutative with identity, and 1, and this AB equal to 0 implies A equal to 0 or B equal to 0. So this is called domain. And why? When it is called PID, PID is principal ideal domain. That means every ideal is generated by a single element. So every ideal is generated by a single element. I is an ideal over any ideal over R, then even the whole ring is generated by the 1, because the domain with 1, and the 0 ideal generated by the 0 element. So like Z is one example of PID. So Z is any ideal of Z is just ideal is just generated by a single element, like say N, so which is NZ, the set of all elements like N which multiply N, so which is Xn, or right. So it's better A into N, where A in Z, so A in Z. So this is called PID, which is also named as principal ideal domain. Now Z is a PID, and we know that any group is abelian group. Abelian group is actually a module over Z. So it's a module over Z. That means a module over a PID. So we actually want to generalize this idea of abelian group. So abelian group is a module over Z. Now we are going to generalize this idea. So module over a more general class of ring called PID. So Z is PID. So then obviously the abelian group is module over PID. And field is a PID. So field, we know that any field is PID. So because only there are two ideals in a field, 0 and the whole thing. And since field is PID, and the module over in that PID, that means the field is a vector space. So basically there is a generalization of this idea of abelian group is a module over Z, and we just restricted our vector space concept in smaller domain. We actually have some take some between some abelian group and vector space, something like that. So which is a nice structure. The ring has also nice structure, and this module has nice structure. And we see in the first video that this is the only ring which has nice structure. Other than that PID or this thing, everything the similar result of vector space is not true. So that's why the module over PID is so important. And one thing, the module over PID must be assumed to be unitary, and we know what is the definition of unitary: 1 into x equal to x for all x in that ring, in that set. That module. So that is called unitary. So that is very important. So that is module over PID. Now, submodule of a free module. So the submodule of a free module. So there is an important thing, important theorem, that let F be a finite dimensional free module over PID, and M is a submodule of F, then M is free. So any submodule of free module is free, and the dimension is less than or equal to the dimension of F. We know what is free. Free is whichever basis, and we know for module over free module, the basis has same number of elements. That is called the dimension, and that dimension of n, the submodule, like subvector space, subspace, as a dimension is less than that the dimension of V. Similar result here. So dimension of M is less than dimension of F if F is finite dimension, but this is true also for infinite dimension also. But that needs some transfinite induction or John's lemma, some chain condition. So we just avoid this proof. We prove it only for the finite dimensional case. So okay, what is the proof? The line of proof is this. The complete proof basis of it. Now we have to. So what we have to prove? So we have to prove that the submodule M, the submodule M of, so it is a submodule. Submodule M is a free, M is free. To show M is free, and basis have at most n elements. So number of element in basis must be less than or equal to n. So basis has at most n. Let's say at most n element. Now, okay, let's take MR to be M intersection the span of x1, x2, xr. Now we're taking just what is R? We are taking R from 1 to n. So we just take, so we take M1, M2, dot Mn. So this is span of x1, x2, x. And what is Mn? Mn is the whole M actually. The span of x1, x2, x is the whole module. So M is the module. That will be, sorry, submodule. So it is the F. F. If we take n, then it is F. So no, the span of this x1, x2, xn, that is F. That means your M intersection F, which is F, M, right? So Mn is M. And what about M1? So generated by just x1, generated by the set x1, just element x1. So it is ax1. Now we'll prove it is on induction. We give induction on R. We'll prove by induction on R. So for R equal to 1, what happened? For R equal to 1, we have this M1, and M1 is like that. Now let I equal to set of all element of R such that ax1 equal to belongs to M1. So take all such A from the ring such so this M1 is actually set of all element like A1 for some A. Actually it is for some A, not for all A, it is for some. So x1 for some x1 is for some A. So what happened? Then what is I? So I is set of all element in R such that x1 is M1. Now I is ideal, and on I is ideal in R. So I is ideal in R. So we know, so the ring is PID. That means it is generated by a single element. So that single element is say A1. For some A1 in I is generated by A1. So it is PID. That's why it's generated by the single element A1. But then what happened? What happened? What about the M1? M1 is actually that element is generated by A1, so it must be generated by A1 X1. So it is generated by A1 X1. So remember that M1 is just M intersection the span of X1. So it is that span of X1 is actually a set of all A X1. But since M1 is M intersection span of X1, so may not be all AX1, like say there may be some A such that AX1 is in the span of X1, but that AX1 may not be in M, so that that is not in M1. So we have to take that A for which that AX1 is belongs to M. In that case, it belongs to the M1 intersection. So that is the ideal, and that ideal divided by A1, and we M1 is just generated by A1 A1. So, and obviously if A1 is 0, then just A1 is if and only if A1 is 0. This A1 is 0. If and only this A1 is 0. So M1 is free because it's generated by single element or is 0. So it is free with basis. What is the basis? If A1 is 0, then the basis is phi. So basis has no element because it's 0 element. So null vector space has no basis. And if it is not null, then M1 has a basis. So basis of M1 is either phi or that A1 only single element A1 X1. According to whatever, if M1 is 0, then it is phi. If it is not non-zero, then it's A1 X1 element is only one element. So we have this proof for this module about free module, the submodule of a free module of finite dimension is again it's free, and with the which element is just one element or 0 element. So this is we prove it for n equal to 1. So we now we're going to the on the induction step. So we assume that there is for each r, we assume that for each r, it is assumption, assume that MR is free, MR is free, and the basis is say BR, and the cardinality of BR is number of element of BR is less than or equal to R. So we assume that it is there are many less than at most are many elements for it, because we assume here for it is true for or R less than or equal to n minus 1. So what you have to prove? We have to prove for R plus 1. You have to prove for R plus 1 that is also free, and that basis has at most R plus 1 element. So idea is now same like for the case of single element. We have to include one more element. So let that Z be the set. Z is a set of all element of ring such that ARX1, AXR1 plus that elements of that from the basis AR, AI, XI, I equal to 1 to R. So this belongs to MR plus 1 for some. It may not be for all. For some in this, because remember this is not the whole spanning set of x1, x2, xr plus 1. It is just a spanning set intersection with the M. So M may contain some elements which does not have this form, or some element of this form AXR plus 1 may not be in M. So the other is not true. Sorry, every element of MR plus 1 that M is of this form, but not MR is of this form, but may not be the other way true. The all element of this form, right in right side, may not be in MN or MR plus 1. So we took only that element of R, and that is again this is an ideal, like the case 1. It is again an ideal, and since it is ideal, it is a single element generated by a single element. Say that is called that is element X AR plus 1 for some AR plus 1. Now again, if AR plus 1 is 0, then this MR and this MR plus 1 is equal. So if XR plus 1 is 0, AR plus 1 is 0. So then it is at no new contribution. So if AR plus 1 is 0, then MR and MR plus 1 is safe. So in that case, what happened? In that case, that m r plus 1 is again free, and the basis number of element of the basis is just a b number of element of br, which is at most r. So that means it is less than or equal to r plus 1. If it is less than or equal to r, that means it is less than or equal to r plus 1. So now the case, if it is non-zero. So if it is non-zero, so what happened? If it is non-zero, that means your ar plus 1 is non-zero, and in that case, similar way for the case of 1, we can prove that that basis element, basis number, this m r plus is also r plus 1 is free, and the base number of element in basis is the just br and one more element, extra element, and it's just the element br plus 1 is the basis of this mr plus 1 is the basis of mr union one single element, extra element. So how do you find that element? X0 is again a basis, and this basis have br has number of element less than or equal to r, so that means br plus 1 has element number of element at most r plus 1, less than or equal to r plus 1. So how do you, the question is, how do you find that x0? X0 is nothing but this element. So x0 is a element which belongs to mr plus 1, such a way that the x0 is of this form ar plus 1 xr plus 1 plus the rest part I equal to 1 to r ai xi for some ai for some xi. So this x0 actually works here, and that x0 we take as a basis element. In this case, we can easily prove that mr plus 1 is nothing but mr, and that the extra part generated by the x0. So this thing you can easily check. Obviously, this mr and intersection are x0. That part is intersection is 0, only 0 element, because this sum is actually direct sum. So this sum is actually direct. That's why it forms a basis, because you need to prove that x0 is independent on that whole thing. So if you include one more element in the basis, that element must be the independent of this other element. Otherwise, it can't be basis. That means you have to take the element from the outside of the span of the string. So you have to take the mr x0, like, which is not in mr actually. So that means you have to take because it is always true, because you are taking ar plus 1 is not equal to 0. So actually it will work for any xr plus 1. No, xr plus 1 is given there, so it is may not be true for any xr plus 1. So xr plus 1 is here given in the past in the basis of that f, and that we got this ar plus 1, and we can easily prove that this x0 is from including x0 is from, say, new basis is a basis of this mr plus 1. Once the basis of mr is given and we have include that x0, we have the basis of mr plus 1. So by induction we can, so by induction we claim that this is true for any n. So this is the outline of the proof, and the details you can find in the book. Now, most important corollary is this: a submodule of a finitely generated module over PID is finitely generated. This is very important, because the dimension is less than or equal to the dimension of that the module. So it is a finitely generated. Again, it's a finitely generated. So a submodule of finitely generated module over PID is finitely generated. That is very important. The idea is again same. So if m is, say, generated by n element, it is m generated by n elements, then we shall show that any submodule m, say n is a submodule. When I write in the subset notation, it is actually submodule generated by n elements or fewer elements. So it can be a lesser number of elements. Now m is we know that m is a quotient of some free module. So it's finitely generated n elements. So m is quotient of some free module Rn. We know in the previous video that if m is finitely generated module over PID, it is actually quotient of some free module. So M is isomorphic to quotient of the R to the N. So that module may not be free. Remember, in the previous theorem, we assume that the module is free. Now we don't assume the module is free. We take only finitely generated thing, and the module may not be free. So we have a thing that modules may not be free, but it is a quotient of a free module of dimension n. So this is isomorphic to this for some PID, where for some ideal, for some submodule of P of Rn. So P is a ideal of, P is a submodule of Rn, and that M can be written as Rn quotient by P that we saw in the last video. That any finitely generated module is a quotient of some free module. So in the previous theorem, what we assume that the module is free. Remember that we assume that the module is free. Once the module is free, then we have every submodule has a free and as well as a finitely generated. But here we assume just the finitely generated, not the free part. So how do you reach this? So we have M is quotient of free module, quotient by some submodule P. Then what happens? Then what is the submodule N? What is the structure of submodule N? So now N is say N. How do you get N? So say Q is submodule of P, and P is again submodule of M. Now we know from the previous some video that if N is submodule of M, then and that since M is this is not true. It's Rn. So P is a submodule of Rn and Q is again submodule of P. Now M, how do you get M? Rn quotient P. So any submodule of that M is isomorphic to this. So any submodule of N, we know the submodule of N is actually the quotient of that Q mod P. Sorry, I write the other way. Sorry. We have to take this one. So Rn is the biggest one. So P is a submodule of Rn, and we take a submodule of Rn, and P is a submodule of Q. So we have to take some between P. If you take any submodule of P, then that goes to 0. Once you quotient by P, and if any submodule of P, that goes to 0, because once you quotient by P, this kills every element of P. So this kills every element of the submodule. That means you have to take the bigger thing, and that N is nothing but that this thing. So we know if any submodule of M is of this form Q mod P, where Q is submodule of Rn. So N is isomorphic to this. That in the previous video we seen that this is true. So N is isomorphic to Q mod P for some Q, which is Q is submodule of Rn and P is submodule of Q. And Q is free. This is free because now Rn is free, and any submodule of Rn is free over PID, because Rn is free over PID. So Q is a submodule of Rn, which is free because the ring is PID. That means Q is free, and Q have dimension must be less than or equal to dimension of that Rn, because Q is submodule. So dimension of Q is less than or equal to N. Now what happened? Is dimension of N, and so that means what? That means Q is a free module over R, and the dimension less than N. That means Q is isomorphic to some Rm. If dimension is M, that M is less than or equal to N. So Q is actually isomorphic to Rm. So any submodule over that free submodule over of Rn is just Rm. is like a vector space. So any subspace of Fn is a like Fn. If dimension of this vector space is n, that's look like a Fn, and any subspace is actually F of the form Fm, actually isomorphic to Fm. So that is isomorphic to Rm. So any free module over PID finitely generated is just behaves like a finitely generated vector space over field. So that Q is isomorphic to Rm. So what happens? So n is then isomorphic to Q mod P. So it is Rm mod P. So isomorphic to this, we have this Rm of submodule of Rn, and P is also submodule of Rn. Now what you get? Rm. So M is just some quotient group of Rm. So that means the Rn has a base. Rm has a basis, and that basis actually, if there is a canonical isomorphism. So we have this canonical isomorphism whose kernel is say P. So there is a kind of isomorphism projection map, and that basis of Rm actually have an image in basis is n. So that means that basis a number of element of basis in n is same as number of element of basis in Rm, so which is n. So then dimension of n is, it is free, it is generated by that image of the basis element of Rm. PID, but it is true for any finitely generated module. We have to go in up. We have to do it on some free module and then quotient. So that is the basic idea of this whole thing. So this correlation is very important. So this is that finitely generated part as a submodule is also finitely. This is not only true for finite free module, it is also true for any module, any finitely generated module, but the ring should be PID. That's the important part. So we just state one theorem. We will not prove it because it needs some work. In next video we'll see what is a torsion module and what is the torsion free part, what is torsion part, torsion free module, and then we have to go for structure theorem of that module over PID, and that actually gives a structure theorem of abelian group. What we done by Silos theorem and other thing for non-commutative group, we actually do it for commutative group using that module theory. But for non-commutative group, we need some that thing, the Silos theorem and group action on set and all these things, congruence idea. But for abelian group, because abelian group is actually module over PID Z, that we can do just a corollary of that special case of any general module over PID. It's a free finitely generated free module. So this result is also true for that any algebra and group theory, and you will see in the group theory that this similar result is there, but this is only for the commutative part. And for commutative part, what is the more general? It is true for any abelian group, but more generally it is true for free module. So if it's free module of dimension n, that we assume in the previous slides, and M is a submodule of F, that means M is also free, dimension is less than or equal to n. And now then F has a basis, say x1 x2 xn of F, and non-zero elements, some non-zero elements A1 A2 AR. Then what is the basis of question? What is the basis of M? So basis of F is x1 x2 xn, and what is the basis of M? Since it is free, we know it is free, but basis is like that. You can't take that x1 x2 xn are the basis, but the basis is like this. So there is some x1 A1 into AR. There is some A1 into AR. We can just reshuffle the basis. Actually, it may so happen that you can take a element xn, say, and if you take the submodule generated by xn, that is not xn. So you have to, there exists an basis. So you have to just reshuffle this basis. So whatever the element in M we took first, the elements of which generates actually F. But that x1 x2 may not be generated. Like say if Z is a free module and then to say 2Z is a submodule, but that one is not the generator of basis of that Z, but one is not the generator basis of 2Z. So 2 is the basis. So it is actually multiple of 1. So that means some number is there, A1, A2, AR of this ring, such that in R, that PID, this is called the invariance or elementary divisors, also called elementary. This is unique. Unique in some sense. I'm going to just say what is unique in one sense. Up to associate, what is the meaning of unique up to associate? So called the invariant or elementary divisor of M in F in that module. So what is the module of, what is the basis of that submodule? This is just A1 x1, A2 x2, N. So R is the dimension of M and N is the dimension of F. So we have to choose the R many element. But why this first R? Because we have to reshuffle them. Then we have to rearrange the basis of F so that the first R is, we can choose first R many elements. And that x1, x2, x are not the basis. Like a vector space, you have a n-dimensional vector space, and if you have a m-dimensional some n-dimensional thing, then we can choose the first something. We can't choose the first. We have to reshuffle all this thing. But we can choose the elements, not the multiple of some, because in the field, if we multiply it by something, it's nothing other than non-zero. That should be non-zero element. That is the same actually. For field, what you take V as a vector or some AV as a vector, where A is the element of F, non-zero element, then these two are same actually. Whether you take V or AV is same, because you just always multiply by A inverse and take A inverse AV is just V again. You can generate, you can find V from AV, you can find AV from V, multiply by some scalar. But here it is not true because inverse may not exist. So you can find A1 x1 by multiply the x1 by A1, but you cannot express x1 in terms of A1 x1 because A1 inverse may not exist. So that's why this A1 AR is very important. In the field case, this A1 AR has no meaning actually. Such that there is again one more condition. Otherwise, it can be unique. You can just rearrange this A1 x1, A1 A2 AR. So and x1 x2 xr, such that if A1 divides A2, A2 divides, this means A1 divides A2, A2 divides A3, dot dot A3 divides A4, like AR minus 1 divides AR. So these are some divisor of AI is divisor of AI plus 1. Such a thing is also happen. So this is very important to find the structure of abelian group or finitely generated free module over PID. This is very important, this theorem. We'll not go into the details proof of that, but this theorem is, application of this theorem is very important. You have to remember two things. You have to choose the R many elements, because the dimension of M less than or equal to N, and that R many elements actually are the multiple of some x1, x2, xn, xr, and that not only that multiple are also some has nice property. To unique, have to be unique. And one thing you can do, you can always choose if some U is a unit element in in R, you can always choose the unit in R means there is a U inverse exists. So you can always choose that other than A1 x1, you can always choose again U A1 x1, because again you can find A1, you can write A1 x1 in terms of U x1 because this is just U inverse. U is exist, even universe is exist. So you can always do this. So whatever, like vector space, whatever you can take, we can take AV or A not equal to 0, because 0 is not the unit element of field, and any other non-zero element of field is a unit element. But here it is not in that case. There are some elements which are not 0 but still not unit. Like in Z, 1 and minus 1 is the only unit element. So other than unit element, but if you just multiply by unit element, you can always do that. You can take, say, 2x1 or you can take minus 2x1. Same thing, because always you can multiply by minus 1. But you can take 4x1. So the spanning set generated by 2x1 and the spanning set generated by minus 2x1 is same, but 4x1 is not same. So that means you can always do. We can always replace A1 by UA1. You can always choose that. So in that case, A1 may not be unique. That's why you will write unique up to associate. You know that if U is a unit element, then A1 and UA1 is called associate. These two are elements called associate, because each can be represent the scalar multiple of the other. Scalar here, you don't use the term scalar. It's just element of the ring. So we can always do that. So it's unique up to associate means, that means if you have another element, say B1, B2, BR, such that B1 divides B2, B2 divides B3, BR minus 1 divides BR, and that B1 x1 BR xr is the basis of Bn, then A1 is associated with B1, A2 is associated with B2, and AR is associated with B2. That is called the unique up to associate. So that's all for this video. Next, we go into the structure theorem.